38. Among other things, an ideal fuel for the control thrusters of a space vehicle should decompose in a spontaneous exothermic reaction when exposed to the appropriate catalyst. Evaluate the following substances under standard state conditions as suitable candidates for fuels. Okay, so the question is, we have hydrazine, right? And hydrazine, which is N2H4 gas, will decompose. It breaks down into its two elemental substances, nitrogen gas, N2G, and then hydrogen gas, right, H2G. The question is, can we use hydrazine as an appropriate fuel for these control thrusters in a space vehicle? Well, they did tell us one thing. They told us that when this decomposes, it has to be in a spontaneous exothermic reaction. Now, if something is going to be spontaneous and exothermic, we're talking about two different variables. If we're worrying about something being spontaneous, there's only one variable that will definitely tell us that. And spontaneity comes from Gibbs free energy, which is delta G. So since we're in standard state conditions, we can go in the back of the textbook to find out the delta G values for each individual component, which is exactly what I did here. So I found out that the delta G for the N2H4, the hydrogen, is 159.4, and all delta Gs for any elemental substances, your diatomics, N2 and H2, they're 0. So how are we going to find the whole delta G for the whole entire reaction? Well, that's this formula right here, right? Maybe I'll just put this a little bit down. Delta G for a whole entire reaction, RxN is reaction, is the sum, that's this little symbol here, the sum, that means addition, the sum of all the delta G products minus the sum of all of the delta G reactants. Now, since we're only focusing on delta G, let's just bring this little delta H down here. We'll get to that in a little bit. Now, will these numbers change or will they be the same? Well, it goes by the balanced equation, specifically your coefficients. You had nothing in front of the N2H4. That means you had only one of them. Nothing in front of the N2. That means you had one of them. And you had two H2s. It's just good practice to take all your values that you have, that you found in the back of the textbook, because we're in standard state conditions, and multiply them by your coefficient. Now, in this case, 1 times 159.4 is going to be 159.4, but it's good practice just to get into the habit here. So that would be times by 1, this is times by 2, and now sum them all up. Literally, in the balanced equation, it was N2 plus H2, sum, that's the addition. So we have to add these two values together. But I mean, 0 plus 0 is obviously 0 total. And I don't have to sum up anything on the reactant side because there's only just the one component, N2H4. And 1 times 159.4 is 159.4. Okay, now we have these values. Let's plug them into our equation for delta G. So delta G for the whole entire reaction would be the product, which is 0, minus the reactant. So 159.4. And I'm just going to put my answer over here because we just need a little bit more space moving forward. So my whole delta G reaction, I mean, if you want, you could plug this into the calculator. Lovely calci on the left-hand side. 0 minus 159.4. I mean, obviously, it's going to show you the negative, right? But just to show you. But we got this, right? Negative 159.4. And that unit is in kilojoules. If you're using your standard state conditions, you're multiplying by your coefficients. Those are your mole values. So if you're taking this and multiplying by mole, the moles cancel, and you're just left with kilojoules. Okay, so we have a delta G answer of a negative value. Is this a spontaneous delta G? Well, remember, spontaneous means that I don't need any additional external energy source to get this going. That's why it's a great, candidate for fuels. And always a negative delta G will be the spontaneous one. Positive delta Gs are non-spontaneous. Since we have a negative here, we're halfway there. This is proven to be spontaneous. Okay. But now, are we spontaneous exothermic? Exothermic comes from the delta H's. So spontaneous, being spontaneous or non-spontaneous, is all about the G's. And exothermic and endothermic is all about the H's, delta H. So I'm just going to maybe write that over here. So we want it specifically to be exothermic. And exothermic, amount of heat that's given off, that's a delta H value. That's why I have these numbers here. And the formula for the delta H is the same as the delta G. So I can just give this one right here again, but instead of all of the G's, I could erase all the G's and replace them with H's. So delta H for the whole entire reaction equals the sum of all the H's of the products minus the H's of the reactants. It's the same formula, but just different variable. So do the same thing that we did before. 95.4 for the N2H4. We got zeros. This can all be found in the back of the textbook, right? Your appendix values. I'm going to take this times by 1. Take these times by the coefficients, just for good practice. Sum up the two of them, but 0 plus 0 again is 0. And this one would be the same number, 95.4. And these are now the two numbers that go into your delta H. So let's go for it. Delta H is products 0 minus reactants, so 95.4. 0 minus 95.4, we know that that's a negative. We could always use our handy dandy calculator to get us there, right? 0 minus 95.4. Boop, there's the negative. But now the question is that negative exothermic or is that endothermic? Maybe I'll box this off first. I heard you. Did you say that exothermic is always the negative? Then you're exactly correct. Anytime that you have a delta H of a negative value, that's exothermic. That means that your heat is being released. On the flip side, if your delta H was a positive, that's heat being absorbed. So here we definitely have a negative. So this has to be exothermic. And it's spontaneous exothermic. So this would be a great candidate for fuels, for, this outer space thing. Candidate, I don't know how to spell this. Candidate. Yeah. There we go. Box that off. And this one is done. What do you think? Okay, thank you so much for viewing the video. Subscribe to the channel if you want to help us out. Tell your friends, tell your classmates about this cool channel. We also have physics and math videos at the moment with much more subjects coming your way in the future. So check back. Love to help you out. Hope you're doing well. Keep studying hard. See you soon. Bye-bye.